Hey guys, welcome back to my channel. Today we are going to talk about the spanning tree protocol, the STP protocol. It's a layer 2 protocol which is generally used to detect loops in a network when we have redundant links. As a network engineer, you would want to create redundant links or something called as backup links, like where in case one path fails, you have another path to route the traffic to. Okay, so there's not much of drop in traffic. So that's why all the network engineers should have redundant links or backup links in the topology. Okay, but sometimes what happens is these redundant links, if they're active, they might cause a loop. Okay, so STP will monitor all these network links. It will identify the redundant connections and it will disable those ports that can lead to looping. Okay, now let me show an example how this can happen. Okay, let's say we have three switches, switch A, switch B and switch C, as I've marked over here. Now switch B receives a broadcast packet. So what's the a layer 2 switch, what will it do if it receives a broadcast packet? It will send that particular packet out of all the other interfaces except the interface it has received from. Okay, so let's say if B has received from a host which is behind switch B, it will send the packet out of the interface. Let's say this is interface 1 and this is interface 2. At A this is interface 1, this is interface 2. At C this is interface 1 and this is interface 2. Okay, so B will send a packet out to A, it will also send a packet out to C. Okay, C does not, so this is the initial step, right, of broadcast packets where nobody has learned each other's MAC addresses. What will C do? C has received the packet on interface 1, so it will forward out the packet from interface 2 towards A. A has received from 1, so it will forward over here, right? Then C receives that packet from A on interface 2 and it will send out via 1, and A receives the packet from C on interface 2 and it will send out via interface 1. Okay, like this B receives the packet again it will send out via interface 2, and the packet which is received from C, it will send out via interface C again. So like this a loop is formed. Okay, the broadcast packet keeps looping inside the network again and over again, so an infinite loop is formed. So this is also called as broadcast storm. So in this situation we need to use the STP protocol. So one of the links is cut down, so the traffic only flows through one path. Okay, and the loop is not formed. The other thing what happens over here is, right, let's say switch A receives a broadcast packet from B and a broadcast packet from C. Okay, now switch A needs to learn the MAC addresses of each switch, right? So it will say that the switch B's MAC address, to reach switch B you have to go out via interface 1. Okay, when it has received directly from B. Now the same packet is sent out from second interface also, and the switch C will receive it and it will send to switch A on second interface. Okay, and A will receive that on second interface. So now A will see that B, to reach switch B, it was interface 1 initially, now it is interface 2. Okay, because of this broadcast storm it will again shift back to 1, right, once it receives the packet again from B. So it will keep happening like this. So there is frequent update of MAC address table, which is not required and which is also wrong. Okay, so that's why we have STP protocol. Now let's say I have a host A over here, okay, which is trying to communicate with host C over here. Okay, C knows that to reach host C it has to go out via interface 3. Okay, now so let's say the packet is received on interface 3 over here, right? Once it receives on interface 3 it will forward on this interface and this interface, right? Now A will send this interface over here and this over here. Now C will forward, since C has that entry in its MAC address table, it will forward it out on the interface 3. Okay, and host C will receive the packet. Now the same packet will also come from switch A, correct? So switch C is forwarding packets which are received from switch B as well as switch A. So it is basically forwarding duplicate frames to host C. So this is also one of the reasons why we need STP protocol. Okay, so now let's see how STP protocol works. Okay, so to understand how HTTP protocol works, you basically need to know a few things. First is So this protocol was developed when we had bridges. Bridges are also basically layer 2 devices. These are like switches only. So that's why all the terminology in STP protocol is it's like bridge ID, bridge port, all of that. Okay. So BID is also called as bridge ID. Okay. This is nothing but it's basically you can think of it as a priority number along with a MAC address. Okay. So let's say the let's say the priority number is 32684 and rest is MAC address. Okay. Then we have over here, let me write it over here, BID is 32684 and the rest is MAC address. BID over here is 32684CC. Okay, MAC address is CC of the switch C. Okay, now let's say every link over here, right, from B to A has a cost. Now this cost depends on the speed of the link. If it's 1 gig, it might be 0. For 1 gig, it might be 100. The larger the bandwidth, the lower the larger the speed, lower would be the cost. Okay, so let's say for our reference, the speed of all of these links is 4. Okay, makes sense? Okay, and now what happens is each of these switches, right, they will form a BPDU. BPDU is also called as bridge protocol data units. These are basically like hello messages which will contain information such as the BID. It will contain the information of it will contain the MAC address. It will contain the cost, the root cost. Okay, the first step is to basically elect a root bridge. What is a root bridge? Root bridge is the master which is controlling all of the interfaces and which makes sure that one of the interfaces is blocked so the first step in this process is elect a root bridge. One device will be a root bridge. Okay, so whichever device has the lowest bridge ID becomes the root bridge. Okay, if all the devices have the same root bridge, which will not be the case, then there are like different tie breaking things we can use. Okay, could be like a device ID, a port number, and etc. All of that. So you see that AA will have 32684 priority number. Okay, and AA. So AA, this is the lowest, right? So what happens is each of these switches will form a BPDU and it will say that they are the root bridge. They are supposed to be the root bridge because the cost to reach them is 0 for each of them, right? But once they, like say A receives a BPDU from B and C, it will see that the cost to reach each other is 0, but it will compare its own BID with the other BIDs of the devices switch B and switch C, and it will say that okay, my bridge ID is lower, so I should be the root bridge. Similarly, B and C switches will also receive the BPDU from A and it will see that okay, A has the lowest BID, so A is the root bridge. Okay, so this way we know, we can confirm that the root bridge is A, right? This is the root bridge. So when switch A knows it's a root bridge, what it will do is it will put its both the interfaces 1 and 2 into forwarding state. Okay, now these two interfaces are in forwarding state. Okay, now what switch B and switch C have to do, they have to decide which of the two ports, okay, let's say this is, again this is 1 and this is 2, which of the two ports have the lowest cost to reach the root bridge. Okay, for B, if you see interface 1 to root, which goes to root bridge, is cost 4, and the other path is via interface 2, which is 4 to C, and then from C to A it's again 4, so it's 8, right? So it will choose the interface 1 as root port. Okay, similarly for C also, to reach the root bridge the lowest cost is 4 via interface 1, so it will choose this as root port. Okay, makes sense. So once they have elected the root port, Now they have to decide which ones will be designated ports and which ones will be blocked. Okay, now basically it needs to see there's only one other path, a backup path to reach the route A via the interface 2, and which is 4 plus 4, right? For B, it would be what, like this, to C, and then C to A, which is 4 plus 4, which is 8. And for C it will be from C to B and B to A, which is also 8. 8 and 8, correct? So it's a tiebreaker. So what do they do now? So it will basically again compare the BID, and it will see that B has the lower BID and C has a higher BID. Okay, so it will make B as a designated port, and it will make the switch C will make the interface 2 as blocked. Okay, now this is blocked. Make sense? Let me just erase this. Right, so first it saw the cost, right? Using the cost we saw that it's a tie break, so we went down to the BID. So like that, I think there are like many different tiebreakers. We have probably priority number, root port number, and etc. Whichever is better, they'll, if it keeps tying, then they'll choose one of the other parameters and see and decide like which should be in deep designated port and which should be in blocked port. Right, now in this case what happens, C will not forward the traffic. C's second interface is in blocked state. It will not forward any traffic. Okay, it will just drop the traffic. So this is how, right, the STP protocol works. Okay, now one disadvantage of STP is, if you see, right, so what happens is the root bridge keeps sending hello messages to say that, okay, I'm still active, my links are active, so please do not break the connection with me, my connection is up. So what is the hello time over here? Hello time will be, I think, 2 seconds. Okay, then there's something called as max age. Okay, let's say a device does not receive this hello for 10 times. Okay, so 10 times into 2 seconds, which is equal to 20. Okay, so it will wait for 10 tries. Okay, if it does not receive a BPDU with the hello message from the root bridge, both switch B and switch C, for 20 seconds, then it means that there is a link down. Okay, once the link is down, what happens is the interface 2 on the switch C will go into listening mode. Okay, where now it will listen for BPDUs to get information on, to learn the MAC address. Okay, it will listen, then it will be in the learning stage to learn the MAC address, and then it will go to forwarding state from block state. Okay, forwarding stage. So once it's in forwarding stage, it will start, it will move this from blocked to forwarding, and the traffic will start flowing. So the convergence time will basically take 20 seconds over here. Okay, and this is 15 seconds listening, and this is 15 seconds, that is learning the MAC addresses. Okay, so once it starts learn the MAC address, then it will start forwarding the traffic. Okay, so 20 plus 15 is 35 plus 15 is 50, so it takes almost 50 seconds. Okay, so convergence time once the link is down is 50 seconds, and this is quite high. This is not acceptable, right? In today's time sensitive network, this is not acceptable. So the engineers came up with a new protocol called as RSTP, Rapid Spanning Tree Protocol. This was a new feature that was developed on top of the STP protocol. We'll discuss about this tomorrow. I'll share a link with you guys on STP protocol. Please go through it. Please look at all the states and all the terminologies, and do let me know if you have any questions in the comment section, guys. Please like, share, and subscribe. Thank you.